what we're going to do today is we're going to go through, definition of what electricity is, or electrostatics, what electrostatics means. We're going to talk about the laws of electrostatics. And we might start on electrodynamics, which is on page 75, but we're not going to get past electric circuits. We're not going to go into electric circuits. So regardless of where we are, we're going to pull up there. We've got some complicated things to talk about, but we've also got a couple of videos that I want to show you. They don't really have anything to do with radiology, but they do have to do with personal safety that you need to know. Electricity can be a little bit terrifying. You look around at a thunderstorm and imagine that those big lightning bolts that are coming down are nothing but electricity. It's startling what electricity can do. So we're going to talk about some things about what happens about this time of the year, atmosphere, and how to protect yourself in a couple of different ways. So what we're going to start with, though, is what we're trying to accomplish in the X-ray tube, in the X-ray system, is to convert electricity into electromagnetic energy. And we talked about the different types of electromagnetic energy that we're going to convert from and to, electricity being from and to the different parts or different types. So we have mainly heat, a little bit of light, and even fewer X-rays. Now, since I wasn't here for the first couple of weeks and I didn't get to go through my intro to this semester lecture, I'm going to talk a little bit about that today. That's my favorite lecture, and it's the very first lecture, the very first class, and the very first semester. But anyway, didn't get to that this year because I was out. But where we get our electricity is from a couple of different places. Of course, we have to have some sort of power plant. So be that a hydroelectric from a dam, be it a coal-fired power plant, be it a nuclear power plant, doesn't really matter. But we have to get electricity from somewhere. And for reasons that we'll talk about later on, the electricity and the power lines that are coming to you is very high voltage. So it's very, very high voltage, and we've got to manipulate that from high voltage to something that's safe to work with, right? You don't want your lights working off of 100,000 volts. But what do we need 100,000 volts for? It was 100 kVp, or I just came that way. Okay, so we need it to make X-rays, right? The lowest energy that you're going to use in making an X-ray is probably, really, with the equipment that we have now, no lower than 55, maybe no lower than 60 kVp. That's 60,000 volts. But what we're going to get from the wall is 440 tops. All right, so the electricity comes to us in maybe 100,000 volts. We convert that to 440, maybe even 220. And then we do some gymnastics and we adjust that, and then we boost it back up to tens or even over 100,000 volts. So how we do that is we get electricity from the power plant, and the first thing that it goes into, and I don't remember if in the PowerPoint I'd mentioned this, but we have to have a means. I usually don't drop this until later in the semester, but we have to have a means of making sure that there are no power surges. So we have a thing that we call line voltage compensation. And this is not this test, so I'll tell you when you need to know the information for this test, okay? This is just kind of introduction to where we're going at this point and for the rest of the semester, and why we need to know this stuff. So line voltage compensation is a way to, let me back up. Let's rewind just a little bit. Before it gets to this point, you've got that thing out on a power pole that if it goes out, there's usually a fire and an explosion. And it may be because a squirrel got into it. It may be because of power surge. What do we call that thing? Transformer, right. A transformer. And it transforms electricity from that 100,000 volts down to the 220 or 110, or whatever it is that's coming into your house. Okay, so that's a transformer. So we got a transformer on the electric pole outside of the hospital. So that feeds the controlled electricity into the hospital system. And once it gets into the radiology suite and it goes into the imaging system, first thing it gets to is a line voltage compensator, and that is just a surge protector. That's all it is. So that whenever the air conditioning kicks on in the hospital, or this time of the year, maybe even the heater, what happens to the light at your house if you're sitting with lights on and you're watching TV and the heater kicks on? Things go dim, right? And we don't want that in the imaging system, so we have to have a way to make it not do that. And line voltage compensation, I said it was like a surge protector, but it works in both ways. It's more like a battery backup type device that gives us constant potential. Okay, so we don't have any kind of power fluctuations. Now, when it goes into that, or after it comes out of that, it goes into this thing, and we're not going to talk about the specifics of this right now, but we've got to be able to take that 440 volts, let's say, and we've got to be able to adjust it, because what do you shoot a hand with? Anybody shot a hand yet? Hand, wrist, okay. Do you remember the KVP used? No. I'll give you a hint. It was not 110. So what do you use 110 for? Chest X-ray. What do you use abdomen? Or what do you use, what kind of power do you use for an abdomen KVP? Maybe 80, 85, right? So we have to have a way to increase or decrease that. We have to have a way to adjust our voltage. That's what this thing does. And this is what we call an auto transformer. And it is a type of rheostat. Now, what's a rheostat? Anybody know? You use them all the time, but you don't usually call them a rheostat. All right, so let's say you've got one of those knobs on the wall that turns the lights up and down, makes them brighter and dimmer. What do you call that? Light switch. Dimmer switch, right? It's a rheostat. It's a rheostat. All a rheostat does is turn up or down power. If you've got a radio in your car and it's got a knob instead of buttons to turn it up and down, that's a rheostat. Okay, so in this case, it's an auto transformer, but because it turns up and down power, it's also a rheostat. All right, so we adjust our voltage here. We don't have kilovoltage yet. We just have voltage. And again, I'll talk about how that works later. But it comes out of that, and we still just have voltage, but we use what kind of voltage? KVP, which is kilovoltage. So we have to have a way not just to increase or decrease the voltage, but also increase the voltage by a whole lot. Okay, so we send it into a different type of transformer. This is an auto transformer. We're going to send it into a high voltage transformer. And I'm going to tell you why the squiggly lines are different between the two later in the semester. I usually, again, run through this all on the very first day. Some people love it. Some people, it just scares them out of their mind and they think they need to drop that day. But I'm not going to get that deep into it today. But this is where we get our kilovoltage. So we get this is also a transformer. So it's a transformer, but it's a high voltage transformer. So we take our relatively low voltage, it may be adjusted from 440 volts to, I don't know, let's say we adjusted it all the way down to 60 volts. Okay, we're doing a hand. So we got 60 volts and then we juice it over here up to 60,000 volts. So it's 60,000 kVp at that point. Okay, so when you make your exposure, well, when you press your prep button, none of this is happening. None of that is going on. What you do have, though, is also coming off the auto transformer. you've got another circuit. This is an X-ray circuit or an electric circuit, but you've got another circuit that has something similar to this, also a rheostat, that it adjusts your MA. Okay, so you've got two different circuits, one for KVP and one for MA. With the MA, you've got select MA stations. So, and why they draw this one like this in the textbook, if you go further into the textbook, you'll see this drawing. But you've got specific MA stations, maybe 100, 200, 400, and 800 MA stations. So you've got set MA stations. So this is going to set your MA, but you're still working off of 440 volts. You don't want 440 volts. What you want is more like 25. And this is a reason, is because of what we're going to be talking about today, electrostatics and electrodynamics. All right, so we got cathode into the X-ray tube, we've got anode into the X-ray tube. So we've got a filament here. The thing about electricity is that if the power measured in voltage gets too high, then it can jump before you're ready for it to jump. Okay? We don't want that to happen in the X-ray tube, because then we start creating X-rays while you're still, out in the room, or, while the patient's not ready. Right? So the filament, we've also got a filament transformer, and the filament transformer is exactly the opposite of the high voltage transformer. High voltage transformer, you had big lines over here, big squiggles over here, and little squiggles over here. It takes the voltage and it increases it to kilovoltage. It's a high voltage transformer. This one has little squiggles over here and big squiggles over there. Reverse that, that would be a low voltage transformer. Right, so it's a low voltage transformer, filament transformer. And again, we're going to talk about how those work later on. So this is whenever you hit your prep button, a lot of stuff does happen. But what's going to happen is when you hit your prep button, you're going to activate a induction motor, and I'll talk about what that means later in the semester, and that's going to spin around and around. At the same time, what you're going to do is you're going to create a space charge of thermionic emissions, hot electrons, charging up the area around the filament to get it to the point where you want it to be, so that when you push your exposure button, those things will jump across the X-ray tube and make just a few X-rays, right? So the reason that I'm introducing this right now is because what we're going to be talking about in this section is electrodynamics. What does dynamics mean? Dynamic movement, motion. You think of somebody who's dynamic, they're moving all the time, right? So electrodynamics, the movement of electrons, but we're also going to talk about electrostatics. And electrostatics is just reverse the words and you've got static electricity, right? So static electricity, what do you think of when you think of static electricity?
Shocks.
Shocks, yeah. You're holding a charge, and then you might release that charge and shock somebody, or shock yourself, one of the two, right? So static electricity and moving charges is what we're going to talk about in the first portion of this. Then we're going to get into the circuit itself, or what components you have to have in a circuit. At the point of exposure, though, you activate this portion of the circuit, and the electrons jump across, complete the circuit, and create X-rays. Okay, so electrodynamics are here. Certainly, you've got electrodynamics going through your filament, but in as much as having tube current, you don't have tube current, you don't have electrodynamics going through your X-ray tube, you just have static, in that you've got all these electrons stored right there before you push your exposure button and release the KVP so that they travel across the X-ray tube. Okay, so electrodynamics, moving charges, electrostatics, stationary charges. We're going to talk about them both. And in that context, we're using them both. We've got static charges that aren't going across the tube here, but everywhere else we've got moving charges. Okay. So with that in mind, the primary function of the imaging system is to do just that, to accomplish all that, to use electricity, to convert electricity into something else. Remember your laws of not electrodynamics, but conservation of energy. We're going to take one type of energy, and with that type of energy, we're going to create a different type of energy. We still have the energy. We're just going to create something different, right? So what we have is electricity provided. We manipulate it through the auto transformer, then the step-up transformer, also through the filament circuit. And the purpose is just to our only purpose is to accelerate these things across the tube at breakneck speed. Is like a miniature lightning bolt, goes from cathode to anode to create those X-rays. Mainly heat, a little bit of light, even fewer X-rays. Okay. So don't get too caught up on questions on this. I'm going to answer those, but not in this lecture. Usually I take about a whole class period, so about an hour and 15 minutes, and go through the entire X-ray circuit. Just couldn't do it this year. All right, so electrostatics, static electricity, stationary charges. And anytime we're talking about electricity, we're going to be talking about the electron, okay? Electricity, electron. We're not going to be talking about positive charges because the positive charges live inside the nucleus of the atom. We can't move them without moving, the entire circuit, right? So your conductors or the wires are going to be made out of something with a lot of electrons available so that the electrons can move. So think of, we'll get to that in a minute. So anytime we're talking about electricity, we're talking about the negative charge, just the negative charge, flow of electrons. They're easy to move. Protons, we can't really move those without moving what it is we're sending the electricity down. So to make a mental connection between electrification, it's not the same thing as electrocution, electrification and ionization. Okay, what is an ion? Charged particle, right? So how do you get a charged particle?
Knock it out of its orbit.
Knock it out of its orbit. Now the electron's a charged particle, but is the atom a charged particle too?
Yes.
Yes, they're both charged particles, right? So in that context, electrification just means that the atom has too many or too few electrons. Okay, so again, in context, electrification is the same thing as creation of ion. I'm not going to say it's the same thing as ionization. That's the process of removing an electron or adding an electron, right? In this case, what we're talking about is the actual storage of that electron, and that being electrification. Just so you know, electrocution, if you hear the guy on the TV, he's been working with electricity, and he's talking on TV, he's on the news, he's on TV, and he said, well, yeah, I was working a puddle of water, and I got electrocuted. Did he? Is that? It wouldn't be alive, right? So what's the second half of that? Fusion, same as execution, right? He's dead, right? So maybe they gave him CPR, I don't know, but electrocution is something totally different than electrification. Electrification just means you've got too many or too few electrons. So there are three different ways that we get to electrification, and we're going to talk about this, then we're going to watch a couple of videos. Again, they have nothing to do with radiology, but they have everything to do with safety. All right, so three different ways to get to electrification. And kind of talk about one just a second ago. Somebody was rubbing their hands together. All right, so if you have carpet in your house, and you're walking across the carpet, what you're doing is you're scooping up electrons from the carpet. All right, so the net charge of the universe is neutral. The net charge of the Earth is neutral. So as you're scooping up those electrons, you're just borrowing the electrons from the carpet. That's all you're doing. So now you've made ionization, electrification of the carpet. It's all positively charged. And you're also negatively charged because you got all those electrons you stole from the carpet, right? So what do you know about charges? Like charges do what? They repel, and opposite charges attract, right? So now what you've got is a situation where the carpet wants its electrons back. You want to give them back, but there may be something preventing that, right? So maybe you're wearing shoes that have rubber soles, and we'll talk about the significance of that probably Friday of next week. But you've got electrification going on between you and the carpet. So you've got then a static charge, and that static charge can be quite high. It can be so low that you don't know that you've got it. So if it's so low that you don't know that you have it, you walk over to the, you're leaving the room, you walk over and touch the doorknob, then you don't even know what's gonna happen, but as soon as you touch the doorknob, those electrons go back into the carpet and everything's neutral again. Remember, everything wants to be neutral, right? So if you have negative charges, carpet has positive charges, you touch the doorknob and they go back into the carpet. But if you scoop up and we'll get there in a second. If you scoop up enough electrons, what we refer to as the electrostatic force can be so high that before you touch that doorknob, and this is when you know that you got a static charge, you get close enough to that doorknob, what's going to happen?
You feel it.
What's that?
You can feel it.
Shock.
You're going to feel it, right? A little bitty light, and if you're slow enough and it's dark enough in the room, you can see it. A little bitty lightning bolt jumps from your hand over to the doorknob. And still you've got that it's equalization of the electrification, okay? So 3 different ways that we electrify. One is by friction, that's rubbing, scooping up the electrons as you walk across the room. All right, now you're charged, and so is the carpet. If you get a minor charge and it's not enough to make the electrons jump before you get to the doorknob, that would be electrification. You're electrifying now the doorknob. That's electrification through touching. Okay, so you even it out as redistribution of the electrons. It's electrification still. You're passing on electrons, moving charges, electric charges. It's electrification, but that's through touching. But if you get close enough to it, you've got a big enough charge that you could shock somebody, then now that's what we call induction. And that's the same thing that you get in a lightning bolt, right? So in lightning, what you've got are hailstones way up in the stratosphere banging around on each other, picking up electrons. That's through rubbing. And then if the charge between the earth and the sky gets high enough, then we have a tendency to think of the lightning bolt coming down from the clouds, but it's really the mutual interaction between the earth, which is an electric ground. It can absorb electrons, and the clouds, and you get relative positive charge on the ground, relative negative charge in the cloud, and you get a lightning bolt. Okay, so 3 different ways of electrifying something, and that is friction is rubbing, induction, we get that jump, that's that spark of the lightning bolt, and then we've got contact, which is a little bit harder to see because your static electric charge is probably not high enough to feel it. So this is what I want to show you and what happens with electric charges sometimes. I'll show you 2 different videos. One is worst case scenario, providing they both play. One is worst case scenario, and the other is if the worst case scenario happens, how to keep it from being too bad. The first case, the first video, the guy did everything wrong In the second video, the girl did almost everything right. So first, what not to do? I guess I'll drop it out.
Small town of Sales, Kentucky. It was unusually cold.
Okay, so before actually I get into this, you ever notice that you don't get those shocking moments in the summertime? It's only wintertime, right? So in the wintertime, what we get is a lack of moisture in the air. Okay, so in the summertime, the moisture is absorbed, or the electrons that you would scoop up are absorbed in the air. And it prevents those static charges from building up, except for in extreme cases, you're just not going to have this kind of issue in the summertime. This is a wintertime thing. So it's very timely. We're getting into winter. It's getting colder. Everything's going to dry out, right? Including your skin. And I'll address that here in just a minute. But you can prevent what's about to happen here. And your demographics are going to be most likely to have this happen. So I'll show you the two videos, and then we'll talk about all that.
Damn. One of its citizens, Curtis Donovan, had to go for an errand and needed to stop for gas. What happened next, you won't believe.
So I was going to this laundry.
We'll fast forward past that.
Got out of the car, talking to my grandmother, and just grabbed the pump, put it right in this little gas nozzle, and started pumping. Just started pumping.
Hang on.
Left
Come on back up
to the
here.
radio.
Notice how he gets out of the car.
Got out of the car, talking to my grandmother, and just grabbed
Let's
the
go
pump,
play
put it
part
in
in
this little
Here in a minute.
gas nozzle, and started pumping. Started pumping the gas. Talking to myself. Got right back in the car. It was real cold. Sitting there, talking to her for not even a brief minute. You know what I'm saying? And listened to the radio, and then turned around, opened the door. Got right back out, leaned up against the car, grabbed the gas nozzle, and that was just like that.
In just a flash, flames shoot out of the gas tank. Curtis narrowly escapes getting burnt. Further damage is avoided by the quick thinking of the store's manager.
Well, we were working, it was a Sunday night and things were kind of slow and I was back in the kitchen cooking and I had a guy here that wanted some food and I made a sandwich. And then I can see something reflecting off the side of the glasses. And then I looked over out the window and could see flames just shooting next to the canopy. So immediately I just turned around, hit the red emergency stop button.
By hitting the emergency button, all the gas lines are shut down. By the time the firemen arrive, the car is engulfed in flames. So, what caused the fire? After looking at the surveillance video, the fire department concludes it was static electricity.
Fire behavior needs three elements. Well, fire triangles to fuel, heat, and oxygen. When conditions are right, static electricity from the clothing can produce the heat that is needed for the fire, that electric spark, which is going to mix with the vapors from the fuel.
Okay. So that's what not to do, and you might not have picked up on exactly what he did. But this next one, you're going to see what almost to do. Could have been better, but it's kind of the same situation. I want you to pay attention to how she gets out of it. She gets back in the car because it's cold. She hears it go click. This tank is full, or about however much you want it. She reaches down and poof. Okay. Now, so why did his car blow up and hers did not? Is that?
The engine was on.
Actually, no. It might have been. It might have been, but that was probably not the problem. What's that? Okay. Well, let's back it up and take a look at how it happened. Okay. So remember, there are three different ways of electrifying, right? So you saw her get out of the car. You never see this happen with older patients or older patients, older people. Okay. She got back in the car, right? So she started the pump. She got back in the car. She left the door open. And that's certainly a part of it. She sat up and then she sat back down. And she got up and she grabbed the pump. Maybe, but this is the issue. Ever seen an old person stand up? You're about to. All right. So let's say this is my car, right? So I get out to keep it going the same way. I get out of my car, say I'm a 70-year-old man. I get out of my car. Do I just turn and stand straight up if I'm 70 years old? No, you will find you lose quad strength as you get older. So your older patients, whenever they get up, they swivel, right? Are they collecting electrons when they swivel? Yes. Absolutely are. But then they're going to reach up and they're going to grab the door frame, and they're probably going to grab a portion of the door, which is made out of metal, right? So they're re-releasing their electrons back into the car, and then they get up, right? So what is their static charge? Neutral. They got nothing. What'd she do? I'm not saying she did anything wrong. It was good for her was that?
Just swiveled and stood
She
up.
just swiveled and stood up. She stood up, sat back down, stood up. Each one of those interactions, she's scooping up electrons, right? So what she did right was this. So gasoline only burns on the surface, okay? I don't recommend this, but if you were to take a container of gasoline with, so much gas in it and stand back and flick matches into it, it's going to go, but it's only going to burn at the surface. It's not going to explode until you throw it on something, right? So the surface is going to burn. So what she did right was you saw her kind of hesitate reaching in to do the thing, right? To release the handle. You saw her kind of hesitate a couple of times. She didn't want to get burned. But what she did was she grabbed the handle to release it so it stopped pumping. Okay? So then she could pull it out, and as soon as all that gas burned off of the pump, it's going to go out. Also, the only place that she's going to have a fire going in her car is in the neck of the gas tank. Mm-hmm. So how do you put out a fire? The fireman just told you what a fire has to have. It's got to have heat, oxygen, and a spark or some sort of, it's got to have oxygen, heat, and,
Fuel.
Thank you. So you got fuel, you got heat already there. If you put the gas cap on, what are you going to deprive it of? Oxygen. It's going to go out, right? So what she did wrong, and it, thank God it didn't cause her any kind of problem, but what she did wrong was the first thing she should have left the pump inside the car. She shouldn't have touched it at all. You ever pull up to a gas station, you see a big red button on the wall, just like what they showed in that first video? There's one of those outside at every gas station you go to. Okay? So you don't reach over and try to turn your pump off. Just go straight over to that button and hit the button. It shuts down all gas pumps. Now you can go over and pull it out. Right? What this guy did wrong, the other guy did wrong, is you can't see it, but I guarantee this is what happened.
Electricity.
He pulled it out and just hosed his car down. Now you got, gas burning off of the entire car. He lost his car.
Static. But I can feel it.
She lost a little hair on it. Might have lost a shirt.
There's some shock, but everything went so fast. And as soon as I grabbed it, the flame.
So there's your public service announcement. Whenever you stop to fill your car up, what do you need to do? Touch your car, right? You can get out of the car. You don't have to, act like you're old and pull yourself up or anything, but touch the car. Get out of the car, touch the car, release those electrons, then go to work. Okay? So you saw pretty much you didn't really see contact, but you saw electrification by rubbing, friction, and you saw induction, both in that video. Electricity kind of be scary.
So that's what happened when you're pushing that car, shopping car, and then you touch the button check.
Exactly. Flip-flops, for whatever reason, I've got a pair of flip-flops that if I'm wearing flip-flops at the store, I'm picking up every electron on the planet. If I reach over and touch my wife, she's swinging at me. It hurts. Let's see. Another thing I'm going to try to do is fill those lights. If you remember which. Not what I wanted to do. Still. Worst strobe light ever. Lights. I'm gonna ask them to just silence those lights. All right. So any questions on that? No? So we might not make it to electrodynamics. So then what we need to talk about are electrostatic laws. And there's three basic electrostatic laws. So there's, we already talked about one, that's attraction and repulsion. Like charges repel, opposite charges attract. So you've got, if you've got the situations we've been talking about where you got positive charges in the, carpet or whatever, and you've got electrons, then they're going to want to recombine and make neutrality. Also, though, if you have an abundance of electrons, the reason that charge gets so great is because if you have enough electrons, then the electrostatic force, that's a word you need to be familiar with, the electrostatic force, and that is the force with which the electrons are pushed, can push the electrons closer and closer together. Remember, we have two technical factors in X-ray. We have KBP and mass, right? So mass is just the count of electrons. But KBP is the power of the electrons to do work, right? That's why we call it potential energy. It's the power of the electrons to do work. And where that comes into play is that the electrostatic force here, with these electrons that far apart, is not going to be the same as two electrons that are further apart. Does that kind of make sense? So it's kind of like you take two magnets and you push them together from out here. How hard is it to push them together? Not very hard, but you get them close together and it becomes much more difficult, right? So kind of the same principle. So as the electrons bunch up and get closer together, that electrostatic force increases. So the first one then is attraction or repulsion. So the closer we try to push these things together, the stronger they're going to try to force each other apart. If you got brothers and sisters, or if you got kids, you understand this pretty well, right? You put them close together, sit them close together in the car and go on a long drive and see how happy you are at the end of the long drive. It's not fun, right? You want to put one on one side of the car and the other on the other side of the car. These are your kids. This is you and this is your brother or sister, right? So, the second one then is Coulomb's law, and Coulomb's law describes that. It's got two parts to it, and it's got a mathematical equation that I want you to look at on page 73, bottom right-hand side. You see it? Okay, that's all you got to look at it. That's it. You don't have to work it. You don't have to memorize it. None of that. That's all you need. All right? So Coulomb's law has two parts to it. The first part, and we just talked about both of them really. The first part is that the electrostatic force is directly proportional to the individual electrostatic charges. Okay, so what does that mean? That buzzing around up here. What does that mean? This is an electrostatic charge. This is an electrostatic charge.
The force is like the distance, I guess.
Well, we're getting there. So I've got one, right? So how much do I have? One. Now I've got two. How much do I have? Two, right? So the more electrostatic charges you have, the more electrostatic charge you have, right? So the more you have, the more you have. That's all the first part of that means. The electrostatic force is directly proportional to the number of electrostatic charges. The more you have, the more you have. The second part is you also already know, and that is that it is inversely, what does that mean?
It goes up, the other goes down.
One thing goes up, the other thing goes down. Inversely proportional to the square of the distance between them. What does that sound like that we talked about in depth on Wednesday? It's inverse square law. That's all it is. It's inverse square law. So in order to have a high electrostatic force, we need a lot of electrons. We need to cram them together. Close, right? The greater the number and the closer we put them together, the greater the electrostatic force. So where do we see that in the imaging system? You see that collection of electrons
The filament.
on the filament. Exactly. A lot of electrons on the filament. What we call that? A lot of electrons on the filament. We got two words for it. It's creation of a space charge or space cloud. Yeah, space cloud, space charge. What's the other thing? Thermionic emissions. Hot electrons. We've taken a lot of electrons. We've crammed them right there. Right? Are we creating X-rays? No, we are not. Not until we hit it with KVP and they jump across the X-ray tube, right? But we got a big charge right there ready to go as soon as we do that. And at that point, what we're going to do is we're going to increase the relative positive charge, increase the relative negative charge, and opposites do what? Attract. Now we've got electrodynamics going across the X-ray tube, right? But that doesn't happen until you hit KVP. All of this is just while you're on the prep button. That thing's getting hot. Now, what's the main thing we create in an X-ray tube? Heat. Right. So, if this is happening the entire time that you're rotoring, what do you not want to do? For a long time, right? You're just burning up your X-ray tube. So, it's one of the ways that we, we shorten the life of the X-ray tube by standing on the rotor button too long. Now, is there a time that you need to stand on the rotor button for a long time?
Yes.
Absolutely. Anybody taking chest X-ray on a kid? Okay. What do?
Move.
They move. That's one. What else are they probably doing?
Breathing on like really fast.
Breathing a lot and moving fast. How about crying? You have one crying on you yet while you're trying to take a chest x-ray? No? You will. You will. Right? How long does it take to get that up to speed?
Instant.
1 second. 1 second. Right? So how do kids cry?
Constantly.
Yes, is the answer. Constantly. But when they cry, you know, they get the huff huffs, right? So the right? So they do that thing, but they exhale for weeks, right? But they only inhale for a split second. So they're crying, they go, eh, and they run out of air, but they're still trying to scream. All right. So if you wait until to hit your prep button or just muscle right through and hit prep and expose all at the same time, what are you going to miss? The inhalation. All right. So you got to be on it in that case. Right. If you're in ICU and you take a chest x-ray on somebody that's on a ventilator, you're going to have to be on the prep button for a little bit so that you can see when the patient inhales. Right. But those are unusual cases, and not unusual in that we don't often see them. It's just most people can follow instructions and hold the breath. So most of the time you want to stay off that prep button because you're just tearing up your x-ray tube. Okay. So let's see. Any questions on that? Don't ask me to redo the kid thing. Kind of got a little sparkles, you know. So for that reason, you know, that's why we call KVP our electric potential. We store the electrons over here in relative electrostatics. And if you're looking at this and you're saying, yeah, you've got electricity going through the filament, yes, you're absolutely right. I can't argue with that. That is electrodynamics. But in as much as it going across the X-ray tube, it's not. So, you know, that's why I'm going to call that electrostatics in that context, is we've got electrons that aren't doing the work that we want them to do. So what is potential energy? The ability to do work, right? So we store them here until we send them across the X-ray tube, and you know, that's kind of why we call it electric potential, KVP electric potential. So any questions on that? What time do y'all start lab? At 10:30?
What's
Right, something like that. What's that?
the third law? The third law?
Oh, the third law. Yeah. You got to guess at that one. And that is this. Oh, I left my demonstration up in my office. So the third law also has two parts to it, and they seem contradictory. One is that electrostatic force, so electrostatic charges will distribute evenly on the surface of a conductor. Okay, so let's say I got a flat wire. I've got a flat wire and we've got electrons. The electrons, you know, if I have two electrons, just have some collection of points. Then what we're going to have is, because like charges repel and push each other apart, they're going to find their own level. Okay, they're going to push each other apart until they're evenly distributed on the surface of the conductor. So I'm going to use water as an example throughout the discussion of electricity. You pour water on the ground, does it just stack up?
No.
No, it spreads out, right? Same thing here. We pour electrons onto a conductor and it's going to spread out and it's going to find its own level. And that level is going to be equally distributed. So if I add more electrons, then what we're going to have is a filling in of the gaps, but there's still going to be equal distribution. Okay. So if I keep doing this, we're going to have the same situation going on.
So you're basically just cutting it in half.
Yeah, and just cut them in half. So then we finally get to the point where they're starting to touch, right, or getting much closer to each other. Okay. So what we're going to find is that the closer they get together, the more we, cram them together, the hotter they get. Anytime you've got a electricity flowing through a circuit, you're going to create heat. So we got a whole bunch of them stuck together. All right. Now, I wish I brought this. Let me erase this and draw this in a different way. Okay, so we got a conductor, and we've got electrons on said conductor. This has got to be the whole one. There we go. We got electrons on the conductor, and they've distributed themselves like so. They've not only pushed each other apart as far as they can go, but they're on opposite sides of the conductor. It's for demonstration purposes only. This, I'm not saying that this is exactly how this happens, but this, makes sense for it. So we've pushed each other as far apart as we can go with it, and we're at as far a distance from each other as we can get. Now, what if I were to take this wire and I were to take it and bend it like that? What would happen to these two guys?
We get really close together.
They get close together, and so they would have a tendency to want to go somewhere else. Right? So the third law is just that, and that is that the electrostatic charges are going to distribute evenly on the surface of a conductor. Stop. Start again. But they're going to concentrate on the portion of the conductor with the sharpest curvature. Okay. Anybody been to surgery? Okay. All right. Next time you go to surgery, this time you were probably pretty enthralled with the wound and what they were doing, right? Next time you go to surgery, pay attention to some of the other people. Because you'll see this at work. All right. So watch periodically, just turn around and look at the anesthesiologist, especially if he's doing a surgery like spinal surgery. So when they're doing spinal surgery, they'll give the patient drugs that are what we call paralytics. They call them paralytics because they inject and you've got to have the patient intubated because it paralyzes the patient. So if they're doing a back surgery on a patient, they want that because if they get too close to the spine or one of the nerves and the patient jerks, you got a problem, right? So they want the patient paralyzed, so they give them a paralytic. But the anesthesiology, medicine has a half-life, right? So you take an aspirin, you get a headache, and the headache starts coming back slowly, right? Because the half whatever you took is still working, but not as well as what it was, at maximum dose. Well, same thing in surgery. At some point, that patient's going to start, the paralytic is going to start working off the patient. So the anesthesiologist has to know that that's happening. And he's got this little device, and this, I found this to be hilarious. Most other people don't find it to be as funny as I do, but I think it's hilarious. So he's got this little box, and it's got two little prongs sticking out of it. And those prongs have a rounded area on the end, curvature. Okay. Inside this box, he's got a 9-volt battery. Also inside that box, he's got a transformer. So that 9 volts, he can boost up to about 1,500 volts. Maybe not that high. That's like electric fence type voltage. It might be, maybe 1,000 volts, something like that. Very low amperage, very high voltage. Basically, what he's got there is a miniature stun gun. Okay. Well, that's not even the funny part of it. Funny part is where he's going to stun this guy. Okay, so he's at the head of the table, right? Everything else is under drapes that are sterile, and you shouldn't be touching those sterile drapes. All right, so he'll take this thing, lift up the drapes just a little bit, we'll put it right there. Ooh. Energize it. It's got a little button on it, and he'll poke the button, and if he gets this, You know, the eyes are closing. If he gets that, the patient's no longer paralyzed. I have to give him more medicine. If there's no response whatsoever, they're good to go, right? For a little while, a little while. And then I'll blast him again.
Wow.
Any questions?